For many people, the MacBook has become the ultimate portable workstation. You have the screen, the keyboard, and the battery life. But recently, the focus has shifted to what happens under the hood. Apple Silicon chips are powerful enough to run machine learning models locally. This means you can run large language models and image generators without sending your data to a cloud server. It offers privacy and speed. However, the software landscape has become complicated. You have PyTorch, JX, and the newer MLX framework. All of them claim to be the best way to run artificial intelligence on these chips. This creates a difficult choice for developers and enthusiasts who want to build applications or experiment with models on their own machines. To understand the performance differences, we first need to look at the hardware itself. Apple Silicon uses a unified memory architecture. In traditional computers, the central processing unit and the graphics processing unit often have separate pools of memory. Data has to be copied back and forth between them. This creates latency and bottlenecks. On Apple devices, the CPU and GPU share the same physical memory pool. This allows for much larger models to be loaded without swapping to the slow storage drive. The question is how each framework utilizes this shared resource. PyTorch is the industry standard for deep learning. It has a metal performance shaders backend designed for Apple hardware. For years, this was the only reliable way to get machine learning running on Macs. It works well for smaller tasks and offers excellent compatibility with the vast ecosystem of existing libraries. However, when you push the hardware with large language models, you hit a wall. The memory management is not native to the architecture. It often requires manual checkpoint conversions or struggles with memory constraints on larger contexts. This means if you try to load a large model, the system may slow down significantly as it tries to manage the data transfer. Then there is MLX. This is a machine learning framework developed specifically for Apple Silicon. It is designed from the ground up to leverage the unified memory model. It eliminates the data transfer latency between the CPU and GPU that plagues other frameworks. Because it is built by the same company that makes the chip, the integration with the metal backend is seamless. It enables the execution of Hugging Face models without the friction of conversion steps. The result is sustained generation throughput that rivals NVIDIA CUDA for specific workloads. In side-by-side latency and throughput benchmarks comparing native MLX inference against JAX and PyTorch on M2 and M3 chips, the difference is stark. Consider a scenario where you are running a Llama 3 model. This is a large language model that requires significant memory bandwidth. With PyTorch, you might see the system swap memory to the SSD when the context window grows too large. This causes stuttering and delays. With MLX, the same model runs smoothly. The research indicates that MLX often achieves 2 to 3 times the speedups compared to PyTorch when using comparable quantization support. This is not just a minor improvement, it is a fundamental difference in how the computation is scheduled and how memory is accessed. What about JAX? JAX is a high-performance numerical computing library that has inspired the design of MLX. It is known for its functional programming style and speed. However, when it comes to native optimization for Apple's specific hardware architecture, it falls short. JAX lacks the same specialized optimizations that MLX has for on-device training and inference. While JAX is excellent for research and academic work, it does not match MLX's performance on Apple Silicon for production-grade local inference. The primary disagreement in the community lies in the specific use case trade-offs. MLX is preferred for raw throughput, while alternatives like MLC, LLM, or Llama.cpp may offer advantages in time-to-first token or lightweight efficiency. It is important to note that MLX is expanding beyond just language models. Recent developments include native support for quantized linear layers and diffusers. This means you can also run stable diffusion for image generation with similar performance gains. Spiking neural networks are also being explored via MLX. This indicates a rapid expansion beyond LLMs into generative AI and specialized neural architectures. The performance gap between MLX and PyTorch is most pronounced in memory-bound scenarios. This is where MLX shines. The unified memory architecture allows for larger batch sizes and model loads without swapping. However, PyTorch is not without its strengths. The MPS backend remains the preferred choice for complex training workflows requiring extensive ecosystem compatibility and mature debugging tools. If you are already deep into a PyTorch project, switching to MLX might require rewriting code. The transition cost can be high. The community consensus suggests that MLX is becoming the de facto standard for local Apple Silicon experimentation. PyTorch's MPS backend is viewed as a transitional solution until deeper native metal optimizations are fully realized. For many users, this means choosing between immediate stability with PyTorch or maximum performance with MLX. Looking at the future, the maturation of Apple Silicon solutions is clear. They are becoming viable, production-grade options for local LLM inference. They offer strong privacy and efficiency. While they still trail absolute NVIDIA performance in raw compute power, the gap is narrowing for specific workloads. The ability to run these models locally means you do not need an internet connection. Your data stays on the device. This is a significant advantage for privacy-conscious users. Future research needs to further quantify JAX's performance on Apple Silicon to determine if it can ever match MLX's specialized optimizations for on-device training. So, what is the takeaway for someone looking to build or experiment on a Mac? If your priority is raw throughput and you are running large models like Llama 3 or Stable Diffusion, MLX is the superior framework. It is optimized for the unified memory model to eliminate data transfer latency. You will see better generation speeds and less memory swapping. If your priority is compatibility with existing libraries or complex training workflows that require extensive debugging, PyTorch MPS remains a solid choice. It is a mature tool that works, even if it is not as fast as MLX. JAX is a powerful tool, but for Apple hardware specifically, MLX currently holds the edge. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.